So we're on. Again, securing the battlefield from cyber attacks is the line of business here that we're talking about. It's obviously something that's near and dear to many people's hearts. Mocana's been around for a fair piece of time. You probably already saw what my bio was, so we don't need to review that. Mocana's been around since 2002. Many of you are already using our crypto backend in the devices that you're using. We're deployed widely. Over 100 million devices is our best guess, because we actually don't know all the places that the government and some commercial entities have deployed our software. Obviously a pretty big list of people that we do business with. And pretty much we're the gold standard for embedded crypto, meaning that we came out of DoD specialized access programs in small embedded devices prior to 2002, commercialized the product in 2002, and it's been pumping along ever since. When we talk about security, I like to talk about trust. Trust is where we need to get to in order to ensure security. The devices need to be trustworthy. The data that they generate needs to be trustworthy. If it's not, then we can't make decisions on the data. It's just that simple. If the data is not coming from a trustworthy source, demonstrably so, how can you make a decision on the data? Obviously, that's what many of the counter, pick your term of choice, technologies are addressing today, is how to manage and manipulate data so that it looks like it's good data, but in reality it's not. And Evidence Stuxnet is probably the biggest, best, most current demonstration of that on a very broad scale, where the SCADA operators were looking at their screens and their screens showed everything good, and needless to say, everything wasn't so good in the background. Obviously cyber, as many of you I can see from your patches, are involved. The idea behind cyber as a weapon of war is relatively new. It used to be called, many different names: electronic warfare, counter-electronic warfare, counter-electronic warfare. I mean, there were a bunch of C's that were in those back in the day, and yes, I go that far back. The idea that we're going to see more of this is just the reality of the world we live in today. If anybody didn't see the outcome of the Mirai botnet utilizing embedded devices as their primary control point and launch point for what is today the world's largest monitored botnet of 642 gigabytes per second. That was what was leveled against 9, and then ultimately that was what was leveled against Brian Krebs. So at the end of the day, we're talking about a significant capture of devices connected to the internet, and while many of the networks that you work on may not be connected to the internet, the fundamentals are still the same, right? If Stuxnet didn't show us anything at all except for the fact that there is no such thing as a protected network. Given enough time, given enough resources, near-peer, nation-state, terrorist, given enough time, given enough resources, they can breach our networks anytime, anywhere. So with that in mind, what are we going to do about it? The attack surfaces that we're talking about dealing with today are fairly in-depth, right? Each and every one of these has an operating system. Each and every one of these has a CPU. Each and every one of these has memory. All of those are attack vectors at the lowest levels. And then going up stack, obviously, there's vulnerabilities in the software as written. There's vulnerabilities in the software as used. All of that comes to bear when the opponents are starting to look at how do they penetrate our devices. This is just an example of where these vulnerabilities exist. You can insert your area of choice into this, and we can do the exact same model. Nothing changes here, right? At the end of the day, unless they are built for purpose devices without an OS, and they are secured against all known side channels, and they're using what I've come to start talking about, which is pre-post-quantum resistant algorithms and suites, we're going to continue to have these problems. And we're not going to be able to replace all the devices that we have out there in sufficient time to not continue being vulnerable to these types of attacks. I probably don't need to go through all of these on a step-by-step basis, but needless to say, attacks against critical infrastructure, attacks against command and control systems have been going on for a long time. This is just the latest round of cyber attacks on those infrastructures. The one that I like to talk about the best is Brickerbot. If you're not familiar with Brickerbot, just Google Brickerbot and you'll find out all kinds of information about it. Brickerbot was an attempt by an individual who was probably on the whiter side of gray, who was very upset with the industry not having done anything after Mirai. At least that was his published intention. So he wanted to prove where this logical conclusion would lie, which is ultimately destroying the equipment at the other end of the attack. And by destroying, I mean not being able to reuse, not being able to reboot, not being able to send back to the factory and re-image. The device was a brick. Throw it away, drop it in the lake, buy another one. And we could do that with a cyber attack. Now, the interesting part about all that is, so Brickerbot is out in the wild. They crucified the guy that wrote it. They're still crucifying the guy that wrote it. But all he was really trying to do was show the world where a logical conclusion of this goes, right? If you can destroy the device at the other end of the connection simply with a cyber command, now and no pun intended, the idea that we can make these kinds of attacks valid today against a variety of equipment is important because that's what we're up against, right? The same code that was written here was captured elsewhere, right? Just like Stuxnet became the foundation for Dooku and Flamer and Gauss and Black Energy 3 and Crisis Overload and a whole bunch of other stuff in pieces and parts. So the bottom line is the code's out there, it's real, it's a real attack that we can face, and we really don't have a good defense for it today. There's nothing in the Brickerbot distribution and injection mechanisms that is easily detectable. And more importantly, because of the nature of the industrial devices and their inability to log effectively, I mean, you've probably all heard the story about my alma mater, the United States Navy, had a little problem with some steering controls, which ultimately had some ships running aground, which is pretty much career ending for a naval officer. They could not tell whether it was his problem. Did he issue the wrong commands? Did the helmsman not do what he was told? Did the control system not function? Did the rudder not move? They couldn't tell. They couldn't tell if it was a cyber attack. Some of you may remember some of the Sea Systems Command work that was done years ago in the fact that maybe ships are big antennas. They're big conductors. There's all kinds of nasty things you can do against the hull of a Navy vessel. So again, it would be nice if we knew that. But due to several functions, like not the least of which is least cost technically acceptable, we ran into a situation where the devices being used down in the innards of that naval vessel were Allen Bradley PLCs, the most prevalent PLC in North America, compact logics, control logics platforms. They do not log. They don't generate syslog. They don't generate SNMP. They don't log. They do have the concept of event recorders, which says rudder moved or rudder didn't move. But that's all they can tell you, and those go to things called data historians in the industrial space. So these devices are not built to log. They were never built to be secured because they were never built to be opened up to the outside world. And yet, we are at this perfect storm, which is, on one hand, we've got Stuxnet proving that, and its derivatives proving that there is no such thing as a protected network. And on the other side, we've got this marvelous thing called big data analytics that has been ongoing now for a long time. What big data analytics is all about is getting more data and making better decisions. That's what people want out of these industrial networks. That's what people want out of the industrial equipment that you're using. And I'm not just talking about cell phones. I'm talking about everything that is connection enabled. Everything that is connection enabled at some level has some information associated with its operation that is useful to an upstream decision set. That's what it's all about. So that's what we're trying to do, is we're trying to show ways that we can start thinking about how to solve for this problem. And my personal preference on how to solve that is using cryptography. Okay, so anyway, Brickerbot bounced along for a little while. Everybody found out about it. Some countermeasures were developed. And then something weird happened. Some of you may have been involved in the fact that 4 major U.S. cities lost power on approximately the same day: San Francisco, LA, New York, and Washington, D.C. They all lost power on the same day. Root cause analysis: random electronic component equipment failure in circuit breakers. I'm sorry. 2 is a coincidence. 3 is not. 4 is certainly not. And while, there's been a lot of back chatter talk on what might have occurred, there's no definitive on this because there's no logging. Nobody knows. The devices were slagged. In fact, in San Francisco, they actually started a fire. The device overheated, blew a breaker, blew another breaker, blew a bus bar, and a fire caught. The central office was destroyed. There was no forensic analysis. And even if there had been one tried, there's no data on which to perform forensic analysis. So we're stuck here between a rock and a hard place with things like BrickerBot, where if they destroy the equipment and there's no operational logging, we're not going to know what happened. That's a problem. Because how do we defend against something we don't understand how it happened in the first place? Right? All right, so obviously some of you are facing a myriad of regulations as well. There's work being done to try and herd the cats, if you will, on all the regulations. But at the end of the day, if you're a multinational or have a multinational distribution, at the end of the day, you're going to get caught up in one of these, right? I put GDPR up there because that's actually causing some serious consternation overseas, particularly in the EU, where it's enacted. And I think it's 20 million pounds per incident, up to 4% of the gross of a company. Not too many CEOs of major corporations can withstand a hit of 4% of their gross product in fine to the EU. So they're looking at their liabilities, they're looking at their risks, and they're finding not good stuff. Most of these platforms are built on some form of a Linux derivative. In Linux derivatives, there's this neat little open source package called OpenSSL. OpenSSL has lots of critical vulnerabilities that have been around for a very long time, and I'm not just talking about Heartbleeds, right? There are all kinds of vulnerabilities associated with OpenSSL. But why do we use it? We use it because it's free and it's there, right? This is what I like to call the easy button, right? It's simply, we're not making good choices. We're not putting our money where our mouths are. We're not paying for the security that we need. And I do this at several presentations, and if you've been to one of my presentations, you may have even seen it before, but everybody in here pretty much have an iPhone or an Android-based device? Anybody not? Okay. So you've made a conscious choice, unless you've been issued it, of course, but you've made a conscious choice to buy a device that is less secure. Does anybody in this room think that that device is more secure than a BlackBerry? It's not. So I've made a conscious choice to call a cab rather than use an Uber app. I don't turn location services on, right? These are the things that we're doing today, and it's across the board. We're not buying the right things. We need to be incenting the vendors, us included, to be doing the right things, to be writing good code and demonstrate it, to be putting it on platforms, demonstrably secure, and most importantly, in some near to real-time or real-time model, actually be able to convey that trustworthiness. And if you can't do that, you're in trouble. All right, so enough on BlackBerries. All right, so manufacturing environments obviously are probably one of the most porous of substances because, again, you don't always get to see all the systems that go in to make that up. And theoretically, DO-178, Alpha, Beta, Charlie, whatever, is measuring systems at the system level. But again, they're only doing that in a reasonably cursory approach until you get to the really high DAL levels. So at the end of the day, when you talk about an aircraft, you talk about hundreds of systems made by tens, if not hundreds of manufacturers who have all submitted documentation that is then validated against a master design in order to achieve a DO-178, an airworthiness certificate. But you really don't know if those devices are secure or not. Particularly in air-to-ground communications, both of the aircraft type and of the consumer type, this has got to be a real problem, right? I mean, we've all heard stories about people being able to hack avionics systems from the in-cabin wireless solutions, and I don't believe that much of that is true. But it only takes one mistake, and all of a sudden you are on the backbone, right? And the military, our military, has done a lot to try and solve for that problem with isolation kernels and separation of network functions, even though it's on one backplane. They're separating it in encryption domains. But it's still not the most secure thing on the planet because it doesn't have an ability to convey trustworthiness. It's measured once, it's installed, and it's operated forever. And the only time it gets touched is if there's a physical update to the system. And I'm just using a plane as an example. You can put your own industry of choice in here. All right, so what is trust? Trust requires a lot of things. I use the cloud approach to this because many of you are having to deal with clouds today. At one end, you've got the device, sensor, field device, actuator, something. In the middle, you've got some sort of aggregation system, right? And at the top, you've got that back-end analytics platform. And there's lots of those out there today, right? For all different kinds of data. But at the end of the day, there's three hops that have to occur here, right? The device generating the data, the device aggregating the data, and the device analyzing the data. That's a pretty standard way to convey the problem set. So what we have to have is trust in each one of these. We have to have trusted identity, and that's not just the user, that's also the device. We have to have trusted boot. How do we do that? I mean, it's a Microsoft environment. Yeah, we've got trusted boot in Windows 10 with a TPM, unless it's virtualized. So we're still stuck, right? Finding a trusted boot model is not the easiest thing in the world. Trusted update. I think everybody by now has recognized that the update process is anything but very secure. Sign and hash is not considered secure today. There's actually been lots of conversations about that, both at the manufacturing level as well as at the oversight level from the government on what is a secure update process. I understand there was a presentation yesterday talking about that exact problem, where we don't have a secure update process, right? Hash and sign is not it. If you think hash and sign is it, go talk to the Ukrainians, because that's what they had on their update process for their PLC's programmable logic. Somebody broke the certificate, somebody broke into the channel, somebody reprogrammed. It was just that simple. Certificates are not the end-all and be-all by themselves. They can be broken, they have been broken, they will continue to be broken. Just ask Symantec. All right, so trusted firmware is another area where very little is being done today. You know, we are measuring the firmware as a function of trusted BIOS or trusted boot, but we're really not doing anything with that value. Same way with trusted boot itself, by the way, is that value is only good to the OS. It's not good to the overall platform. If you consider that the operating system is the entire platform, I would encourage you to think again, because it's not. Side channel attacks can occur pre-boot, post-power on. Side channel attacks can happen in memory. Side channel attacks can happen up against the stack itself. All of those things exist today. So what do you do about it? Well, you got to get to some level of trusted operation. That's what we're trying to get to at all levels of this. And you could add the network into this as well, right? There are networking solutions out there that can be added to that trust. The only thing I would point out is that if you're using strong cryptography, the network becomes plumbing, right? So while it's still important and it sure would be nice to know that it's secure also, it's not a requirement, particularly when we start talking about external communications. Okay, so how do we implement a device-to-cloud trust model? First, we have to harden the endpoints, right? Which means using some form of strong identity. And one of the problems our industry has today is that X509 was pretty much at its limits in terms of broad-based distribution. So new identity mechanisms were being developed that are not standards-based. And there's a number of companies out there that do that. Even Intel has joined that game with EPID, right? EPID is a unique identifier that Intel builds that is unique to Intel. Is it cryptographically unique? Sort of. Can you attach a certificate to it? Yes, you can. Is it a hard root of trust? Sorry, it's not. So the idea that we have to harden this requires X509, but the problem with X509 has been, how do we distribute those certificates? So about 7 years ago, a number of industry players got together. Cisco and Aruba actually took the lead, and they developed RFC 7030, called EST, Enrollment over Secure Transport. If you haven't looked at it and you're in this line of the side of the business, I would encourage you to do so. It is basically SCEP over the wire. You heard me. It's basically SCEP over the wire. It solves the problem of multi-mode distribution of certificates across a broad distributed base. There's two pieces to it. There's a client-side component, there's a server-side component. Server-side component sits co-resident with the CA. The CA then creates a certificate through its normal process. It pushes the CA, the certificate now created, the CA pushes the certificate to the EST server side, which then wraps it with additional definition and information about destination. And then it pushes it to the endpoint over secure channel. All of that is then revalidated at the endpoint and then updated as appropriate, with appropriate feedback back to the CA as to the result of the installation of the certificate, yes or no. So again, lots of new technologies coming to bear. That RFC was ratified 3 years ago. You'd think that the CA vendors would glom onto that and run with it. Nope, not doing it. Don't ask me why, I have no idea. I've talked to most of them. They all give it a nod, they all say, yep, it's great, but nobody's doing anything. I mean, I think even Cisco's only stood up 4 functions in EST for their internal architecture. I'm sorry?
Is there a performance hit?
No, it's just like installing any certificate. The problem with SCEP and OCSP is, in order to do it securely, you either have to bring the device to OCSP and SCEP, or you have to take OCSP and SCEP to the device. Am I too high or too low? Okay. So SCEP is a well-understood, a well-defined way to distribute and deploy certificates. The problem is it doesn't scale for exactly that reason. You're not going to bring hundreds of millions of devices into an enclave, and many of you have to deal with private enclaves from a certificate perspective, so even more so, you're not going to bring those devices into your private enclave in order to install a base certificate. Just not going to happen. So EST is what I would consider the savior of X509. X509 is well understood. Everybody understands what it's capable of. PKI, biometrics, there's all kinds of things that we can embed and ensure inside the certificate. Anybody in here still having a problem with SHA-1? Okay. Wouldn't say if you were anyway, I got it. The problem with SHA-1 is we can't get to the certificates. We can't make the changes. If we could get to the certificate, we could remove or loop SHA-1 into some stronger hashing algorithm. Don't negotiate to SHA-1. Negotiate to SHA-2 or negotiate to AES. Don't negotiate SHA-1, but you have to get to the certificate to do that. Or you have to get to the crypto stack to remove the algorithm altogether. All right, I've said enough about hardening endpoint devices. On the end devices, once we have a root of trust created, then we've got to know that it's secure from power applied. Mocana plays in the from trust anchor actualization all the way through application execution. There are still holes in that model. Obviously, there are side channel attacks at the hardware pre-initialization. It's a very small window, but it only takes a millisecond. And there are side channel attacks. There are also businesses out there that are now making that their business to prevent those kinds of side channel attacks. And then there's memory. Memory's another problem, because remember, the memory CPU combination is always clear text, almost always clear text. In the unclassified environments, always clear text. How about that? The point there being is that when it's clear text, that means that somebody who has physical access to the system can manipulate that. Same way with all the firmware and software trust anchors. The only trust anchor that's out there today that cannot be manipulated in the open market is a TPM. There are 6 manufacturers of TPM across the world, including one Chinese that we don't need to talk about. So 5 westernized TPMs in 90% of all client-server computers today. I don't know what the wireless access point here is, but I'm guessing it's either Aruba or one of its competitors. The back end of Aruba, we do. We're the management channel, crypto, for the back end of the Aruba access points, which is great, except that your connection to the access point is on you. If your device is untrustworthy, you can connect to a trustworthy device, doesn't help you much. So these are the kinds of problems that you need to think through when we start talking about securing the process. It's an end-to-end process. So securing the boot process, securing the update process, as we talked about, needs to be a lot stronger. We do some of that, right? What we said is, look, we have crypto. Why not use it? Why sign and hash? Sign and hash is easy. We hit the easy button again. In this model, we don't have to hit the easy button. The crypto's already there. Let's use a PKCS envelope. Let's put the update, hardware, firmware, software inside the envelope. Let's encrypt the envelope. Let's use not just one signer, let's use multiple signers, a 2 or more man rule associated with the update. So Infineon says we're going to update our TPM, and they sign it. And it's part of an Intel subsystem. Intel signs it. And it's part of a Dell gateway. Dell signs it. And then ultimately, the consumer signs it because they don't want stuff going into the network that they don't know about. We need to be able to enforce all 4 of those signatures on the cryptographic container before we open the container, before we install the update. We can do that using cryptography. You can't do that with sign and hash. You can only do one cert, one hash. That make sense? Okay. Integrate the hardware and software-based roots of trust across a variety of ciphers. You know, again, what I've started to call the pre-post-quantum world is occurring as we speak. Right? CNSA is the likely replacement for Suite B and possibly beyond. That's cool. You'll notice what they did in the requirements is they removed some ciphers and they added some ciphers and they did some interesting things to key strengths associated with padding and with entropy. They made it a lot harder to crack those keys. Are they still crackable? Well, we really don't know what quantum is going to do to the cryptographic world yet. We have some ideas. The math is being proven as we speak. Some of you may even be involved in that. The point being is that we really don't know an outcome there yet. So all we can do is strengthen what we have. Elliptic curve is still pretty good. It's not foolproof, it's not hacker-proof, but again, nothing is. All we can do is advance the state of cybersecurity, and we can do that incrementally. All right, so integrating the hardware and software roots of trust across a variety of chipsets as well, right? We've got hard anchors, we got soft anchors, we got firm anchors, right? If you look at a TPM architecture, a hard TPM architecture, you can take that all the way up to FIPS 140-2 level 4. Pretty darn strong. If you look at firmware, you can't do that. Best you can do is software level, FIPS 140-2 level 1. Same way with software. So you really can't get to higher levels of validation unless you're using a TPM. So in the models of industry, when we talk about IEC 62443, particularly the 3-3 area, that's the European standard for industrial cybersecurity, or you look at the NIST framework with the extensions for critical infrastructure and the new guidance that's coming out with both keys, identity management, and the new extensions that are being added under 853 R5, I think. All of those are becoming part and parcel of the things that we have to validate too. So when we do that, we can do that in any number of ways. The point here is that if we consolidate all of those functions, right, and that's really what the Industrial Internet Consortium is trying to do, and full disclosure, I'm on one of the IIC working groups associated with this work. So the short answer is we can take all of those requirements, bundle them together, and give you a best practices document or a a mechanism by which you can evaluate what your environment is, right? If we're talking about low, medium, and high, we can talk in those terms. If we're talking about 2, 3, or 4, we can talk in those terms. They're very similar. Very similar. So all we have to do is consolidate those, hand them to the people that are implementing them, hand that to the people that are reviewing the implementation for certification or for validation, and now we have a solution. And then last but not least, use communications as the means to control access to those devices. And I mean secure communications. I mean encrypted communications. Now, wouldn't it be great if in the traditional TCP/IP stack, 65,535 ports, you're only using one? And wouldn't it be nice if the only way that you could do that was if you were part of the Cipher suite and part of the encryption domain and part of the authentication domain that allowed you to do that? And the only way that you did that was based on both devices being trustworthy. That's what Mocana does. That's my sales pitch. So at the end of the day, that's how we can do this. It's been tried before. I was actually in Redmond in 2008, I think, when they turned on IPsec everywhere, using the domain controller as the arbiter. Everybody got a cert. Everybody was logged in through the domain. Everybody was enrolled in the domain, servers, workstations, users. Everybody was in. And it was great. IPsec everywhere. The only way you could connect to one of those devices is if you were in the encryption domain for IPsec and you were in the authentication domain that the domain controller knew about. Didn't even have to go to Kerberos. It was just connection-based, which was great. Except they forgot that they broke every network management and monitoring tool known to man because everything was encrypted. Whoops. They turned it back off the next day. The Redmond campus was on for 24 hours. Again, these are the problems that we still have yet to solve. What I'm talking about doing is point-to-point trust. All of your network management and monitoring can still go on. We can do SSL, we can do IPsec, because the only communications that are involved here from a trust perspective are point-to-point, peer-to-peer, machine-to-machine, client-to-server, server-to-cloud, client-to-cloud. Doesn't matter. If we're using strong cryptography and effective key management in that creation of those authentication, authorization, and encryption domains, we have a solution. It's not an easy solution to do, but we have one. And it solves for a whole raft of problems that we deal with today in terms of attack surface. The only way you can connect to this thing is either through the update service using cryptography or through a connection service using cryptography. All of a sudden, the answer gets a lot easier. We only encrypt and connect when we're trustworthy. That's a shared value. So what X509 trust chaining allows you to do is through an endorsement process from that root certificate all the way up through the BIOS, all the way up through the bootstrap loader and the bootstrap and the kernel load and the utilities load and the application load and the application execution, all of that code being signed, we can enroll that into a trust chain. At the top of that trust chain, you end up with a single cryptographic value that represents the trustworthiness of the platform at that point in time. That can be done at interval, that can be done on demand. In high assurance environments, that could be done every cycle. Now, that does have a performance overhead, but it can be done. We've proven to do this. Not easy, but it's a solution to a whole raft of problems that we're still struggling with, and it solves a lot of our old problems. So, something to think about. That's what my presentation's really supposed to do, is give you guys something to think about. And ladies, I didn't mean to separate you. All right. Okay. Sure. Yeah, we're coming up on, I'm going to leave this open for Q&A at the end, so we're just about there now. Go ahead, Mike.
So one of the attacks that people are always concerned about, and talk about this through the trust chain, is the attack where you have somebody that becomes the trusted instance. Now everything that they're doing is in a security envelope.
Okay.
So the difference between many of the cryptographic architectures that would through that?
Sure.
There's a way.
There is a way.
This breaks that insider, that trusted insider.
Well, at the end of the day, what's the trusted insider trying to do? He's trying to modify something. Because that's the only way to make an impact. He has to modify something. At the point of modification, the cryptographic value changes. The trust chain is broken. That device does no longer represent itself as trustworthy. You want to take this to its logical conclusion, we lock it. We don't allow changes without two men being involved. We can put a two-man certificate rule into every change of every piece of hardware, firmware, software in the stack. Yeah, wow. We can do that. This is better than whitelisting. This is better than antivirus. This is better than intrusion detection prevention. This is better than behavioral analytics. This is better than anything you can think of, because what I've given you is a binary decision. It's good or it's not. It's good to the strength of the cryptography or it's not. Now, again, if you choose SHA-1 and RSA 1024 as your exclusive cipher suites, you get what you pay for. Yes, it can be easily broken. If you're using ECC and AES, not quite so easy. So this is our stack, and again, I'm using this more as an example that it can be done than I am trying to sell you on something. So the idea is someplace down here at the bottom, you've got a root of trust. And in that root of trust, you may have additional trust functions like crypto acceleration, and that could be on-chip, that could be off-chip. That could be a PCU or an MCU in an ARM architecture, or that could be a Cavium offload processor for the network. Doesn't matter. At the end of the day, we need to band all of those trust mechanisms together in order to create that trust model, which is the root of trust for the platform. Again, this is device, field device, this is gateway, this is cloud.
It crosses OT and IT.
It does cross OT and IT, although in IT this becomes a little more difficult just because the sheer bloat of IT devices. Being able to sign and hash all of the applications and all of the executables on a traditional Windows platform with 1 point something gig of bloatware on it becomes a little more difficult. Yes, sir? What do you mean, not rewriting it? It is ours. It is commercial code. It is not OpenSSL. There is not a single bit of commercial code, of non-commercial open source code in here. You bet. And we are a fit form and function replacement for OpenSSL. We wrote a shim layer. You can literally compile out OpenSSL and you can compile us in. We're 1/8 the size and an order of magnitude faster. But we cost money. We're not free. Okay. Somewhere along the line, you have to bring all these pieces together. We do that through an abstraction layer. That abstraction layer is open APIs. You can call them yourself. You can leverage our use. Above that, we do have the ability to do two things: to participate in a trusted boot sequence if one already exists, again, so that the operating system by itself is not the only consumer of those trust measurements. We want the whole stack to be participating in that trust measurement. If one is not present, one will be provided for you. We can actually do the measurements themselves. We can do the hash measurements and signage for the firmware and validate it at every boot. We can do all of the bootstrap loader, and kernel load functions without the manufacturer signing. We can provide the signing keys. We provide a complete cryptographic stack. And again, we're not the only ones doing this. We're the only ones doing this as a platform that I know of. And I've been at this a pretty long time. Nano Update, we've already talked about. That's a secure update facility. All three of these platforms operate independently. They're all firmware-based. All the rest of this is compiling code. To your question, the cryptographic engine, all of the certificate interface, and all of the cipher suite interface is written by us. Certified to FIPS 140-2 Level 1 and fully authorized for Suite B. So additional review has been done.
You can carry SCI information.
We can and do. High side.
Dean, the commander's consistently been pressing to say.
By the way, he's not a plant. I just know him.
Expeditionary has two things we have to consider. It's got to be fast, it's got to be simple.
Michael, the big answer to that is it depends, right? If you want to use all the cipher suites that NIST approves, it's going to be slower than if you're using just AES and ECC, right? VP of Engineering, who I've worked with in past lives as well, and I actually did a mental exercise here not too long ago. How low, how small could we actually make this? With just RSA 1024, because remember, these are all compile time options. So with just RSA 1024 and SHA-1, 130K. Yeah. We're tiny. We came from tiny, we're still tiny. That's part of what our value is. We write small, very efficient code. Yes, sir. Oh, we're at a time? Okay. Let me just finish through here real quick. So yes, IPsec, yes, wireless. There's included as an option NATO 2.11i supplicant. One interesting thing here, if any of you are dealing with peer-to-peer environments using group keys, which is typical of very, very tightly constrained environments, where they're doing peer-to-peer communications, typically over UDP. GDOI, which is group keys, was created so that there is one KDC and multiple public keys in the same domain. So there is an authentication domain based on a very lightweight public key match. There is not a cryptographic handshake per se between the devices. All they do is validate that I've got the public key, you got the public key, therefore we can talk. And it's an RFC standard, I think it's 5538. But again, because it's lightweight constrained environments, we're talking UDP. So anybody can listen to that key exchange that's going on public key to public key. Not very secure. We created an encryption layer, a very lightweight encryption layer for UDP, specifically for unicast and multicast. That can leverage the group keys that now you have an encryption domain associated with that authentication. SSL, SSH is pretty straightforward. This is EuroCSP and SCEP stuff. NanoAid is the EST functions that I've talked about, right? So we have a full EST compliant client in the architecture. We actually, in an effort to try and get people using this, we've stood up an EST server utilizing the Microsoft GitHub solution, which we've dusted off and modernized and tweaked quite a bit, that we have standing up in a DMZ. So your cert, our EST server to an EST client, you can demonstrate it online. You could play with it. Ike, so that we put Ike in a different module because of all of the new functions that I just talked about. Ike v2, new key entropy functions, new key padding functions. We stuck all of that in the Ike module. And then EAP is everything else under the sun, from extensible authentication, from MS-CHAP to radius diameter. And then all of the upside interfaces of that can be in C, C++, Java, or Python. We're written in native C, so we can do native C directly. C++ is interpretive. Java, we provide the JCI environment. Python, we provide the JCI environment for the backend. So you can interface this any which way you want. In the efforts of time, I'm not going to go through all these. I put a couple of use cases up. Device enrollment using the EST server is exactly what I just talked about, right? You generate a certificate, you send it to the EST server goes out, does all the validation, integrates it with the protected key, in other words, endorses it so that it then becomes part of the key architecture of the target environment. It's validated, it's active, feedback goes back to the CA to say certificate installed successfully, excuse me. Again, this is the reality, and I guess we're making the slides available, so you'll have access to these. You know, this is how we establish a chain of trust using cryptography. It's everything that we just spent 40 minutes talking about. Let me know. Yes, sir?
Hey, what do I do if my devices can't take cryptography?
Back up a step, right? Again, in the efforts of trying to secure things, brownfield environments may not be engineered to where they can take a cryptographic stack. They may not have enough space or horsepower. Go back up a step. Go to the networking devices or go to the gateway services, right? Back up. And if that doesn't work, then back up further, right? Wherever you can start the trust channeling is far better than what you have today. Does that answer the question?
This represents maybe X order of magnitude in creating assurance
No. And it would be really tough anyway. There's over 1,000 compile time options in our stack. So again, lots of adjustability in terms of what you want in the stack. Part of the value proposition would be what you're using. So you'd have 1,000 options right out of the gate that you'd have to consider. And that's just one device utilization, and then you'd have the next device utilization, because in order to actually evaluate its value, you'd have to evaluate it connected to something. So 2 devices connection that would all have to be considered in that kind of a model. I have not done that. And again, we've talked about secure update. And again, we've talked about secure operations. Notice that when we talk about cryptography, we talk about lots of different mechanisms out here. TEE Trust Zone is the next step up from a TPM, right? A lot is being done by ARM and at the design level, and then ARM is being even further enhanced by the silicon vendors, right? So Qualcomm and Ansys and all those guys that are building systems based on the ARM technology designs are adding functions to those. Right? But at the end of the day, we want to take advantage of those. We want to include all of that as best we can into our trust evaluation, our trust measurement, and ultimately our decision on trustworthiness. Is that device trustworthy, and is the data that it's generating trustworthy, or isn't it? You have a puzzled look on your face. Can I answer something? These? That's just the certificate. Again, what we're trying to show here is that all of this is cryptographically based, all of this is certificate enabled, all of this is certificate validated. Every step of this way, through the endorsement process, the vertical trust alignment of the device, and the horizontal means to convey. Yes, sir?
So in this environment, I'm probably going to be in some sort of hybrid type state, especially if it's a brownfield rollout. What are the risks specifically to operating in the state? Is everything inside, where I am working inside this cryptographic environment, secure? And as I roll things out, what are the risks as I expand and do things in the network? So I'm not going to do this overnight.
True.
These are huge networks. I probably won't, from my experience, probably don't even know all the things connected to my network and won't find out until they stop talking to it because of this. But what are the risks during that period where you're doing the transition from your legacy to this?
Well, first and foremost, you may find that your vendors are already doing something along those lines. So the risk of implementation is the risk of you implementing a new technological base function into your environment. So whether it's ARM or Intel or Ubuntu Core 16, really doesn't matter. We've got 70 processors and about 30 OSs that we've ported to currently in many, over 2,000 combinations. Wind River, so we had a customer that came to us and said, look, we really got to get this OpenSSL stuff out of our environment. We've been using you guys for years. We do a make file, we move it into the IDE for VxWorks, works like a champ. But we're in situations now where we don't want to move into the IDE. We want you to already be there. We said, okay, ask Wind River. In the meantime, Intel's an investor in us. We went the back channel, they went the front door. We met at the middle with Wind River. 3 months later, we are in VxWorks 6.9 and above. So if you're using a VxWorks environment, the hooks to use us are already there. All you have to do is write the check. Yes, sir?
Say down the road, I wanted to switch out what cryptographic primitive is being used.
Mm-hmm.
With your platform, can you do that, or that just becomes an update?
Reliant on 2 things. One, does the cipher interface exist, which is a compile time option? If it exists, does the certificate support it? If it exists, then the answer to your question is all you have to do is change the certificate parameters. If it doesn't exist, then you're talking about recompile or update to the platform. Yes, ma'am.
So you're demonstrating all of the products that you all work with on that slide?
Yes, ma'am.
Okay, so I'll point this out. I'm with Safe and Assured Technology,
Mm-hmm.
which is the Bokai company for the Motel.
Mm-hmm.
So in this case, it should be working with Safe and Assured Technology.
It is.
So, okay, because you only have your Motel up there.
Well, you are correct. You're, aye, ma'am. Aye, ma'am. Questions? I mean, this is pretty much the end of my presentation, and we got about 10 minutes left. Kind of been answering them as we go, but any burning desires to have a different conversation?
Well, maybe a little different. I'm really not an expert in device, but you've been talking about device trust,
Mm-hmm.
right? And you made a comment about trusting the data on the device.
Mm-hmm.
So I'm curious as to how, by virtue of trusting the device, you can say that data is trusted.
I can say that the data that that device generated is trustworthy because it came from a trustworthy device. And I said that we could convey it in trustworthy format because that horizontal trust chain is tied to the vertical trust chain. You can't connect to this platform unless you are also trustworthy.
I missed
Yeah, no, it's the data generated on the platform as a target of evaluation.
I'm looking to break your trust chain. Can I do that by knocking out the availability of some of the authentication, not authentication, but some of the certificate servers along the way that are part of the trust chain?
That would be a policy decision on whether you wanted to trust a certificate that could not be validated that was previously trustworthy or not. If it's or not, then the device is no longer trustworthy. If you do, then the device is trustworthy as of the last certificate installation and validation.
So just to make sure I'm understanding you and you're understanding what I'm saying, if I look at that chain and I go up the stack and I say, you know what, all I need to do is knock out one of the, think of it like a PKI model, like a, revocation
I got you.
top. So you have trust, boom, it gets kicked out.
Yeah, I got it. So again, first of all, we're talking about industrial environments. So generally the registration/validation authorities are going to be within these environments. They're not going to be separate. So knocking them out means that you have to be in the environment. Okay, it's not like being able to discontinue connections to a remote CA. The way that these models work is that validation is local, traditionally, because those networks do not have a lot of external, if at all by design, external communications to a root CA. That make sense? So that's issue number one. This is not IT. This is primarily OT. Is it applicable to IT? Yes, we've talked about that already, right? In the OT world, these types of services are already resident. They may not be co-located, but they are already accessible and addressable within an environment. That's how OT works. So you have a registration authority or you have remote validation authority built into the subsets or subnets.
If I understand this right, you're essentially through the cryptography providing binary, trusted, not trusted, feedback to whatever the policy engine is. And
That's
the
correct.
policy engine then dictates whatever I choose to do with that if it's not trusted.
That's correct.
Okay.
And there's some things that we can do, that we know how to do, right? If it's not trustworthy, we can say, do you want to suspend the certificate? Do you want to ask the CA to revoke the certificate?
Whatever you choose, you did
Do you want us to reset the TPM, blow away all the cryptographic material on the platform? Or in a very high assurance environment with our relationship with Intel, we could actually blow the circuit breakers on the Intel processor, thereby alerting the platform. Those are things that we know we can do. More importantly, from a policy perspective, is the things that you might want to do, right? You might want to move this into a quarantine zone, or you might want to disable the interface so that you could do whatever forensics you are able to do on a live system that has not yet been additionally modified or pivoted from.
Okay, I just helped you to understand that in very simple terms. Gotcha now.
Yeah, so we're going to generate a bunch of additional services as a result of this. The stack is done. Everything that I've talked about here today is GA'd and functioning in industrial environments today. Policy stuff, the server-side stuff, we're still working on, and we're still waiting for several patents to be, or I'd be talking about them today. But we've already got pretty much the design of what we want to do from the as-a-service perspective. Update server, so you can do a many-to-one, right? Put the update in an update server, have it do all the negotiation with the clients. EST server, we've already talked about. And then the policy engine itself, and then potentially some analytics of the stuff that we generate for ourselves that may be of interest to others, right? Cryptographic handshakes. Somebody attempted to connect, they didn't have the right key. Who were they? Why did we deny them? Those are all functions that are not traditionally collected on these devices that we're going to have by nature of what we do. Anything else? Going once, going twice? Thank you for your time. Hopefully you found this useful.
Thank you, Dean, for your time. FCO by policy does not give